Welcome to solverfy.
So we want to find the position as a function of time of a simple harmonic oscillator, but we must use the law of conservation of energy. So we can say that we can start off by saying velocity is going to be equal to plus or minus the square root of the spring constant divided by the mass times a squared minus x squared. So that would simply be the formula for the velocity. Now this is going to equal dx over dt. This is simply the definition of velocity, a change in position over with respect to time. Therefore, dx divided by a squared minus x squared to the positive 1/2 power is going to be equal to plus or minus the square root of k over m times dt. And at this point, we can actually integrate and say that um, the integral from x naught, let's move this, the integral from x naught to x of dx over a squared minus x squared to the 1/2 power. This is going to equal plus or minus the square root of the spring constant divided by the mass times the integral from 0 to t of dt. And so we can say that this, rather, we can actually evaluate at this point and say that negative arc cosine rather, of x over a evaluated at x naught and at x is going to be equal to plus or minus the square root of k over m times t. And we find that we can express this, we can expand this rather, and say negative arc cosine of x over a plus arc cosine of x naught over a will be equal to plus or minus t times the square root of the spring constant divided by the mass. We know that the angular velocity is equal to the square root of the spring constant divided by the mass, and we know that the arc cosine rather of x naught divided by the amplitude would be equal to phi, the phase constant. Therefore, we can say that negative arc cosine of x over a plus phi, the phase constant, is going to be equal to plus or minus the angular velocity times the time, and rearranging and isolating x is going to be equal a cosine of plus or minus omega t, so the angular velocity times time, plus the phase constant. And this is the general formula for a simple harmonic oscillator. That is the end of the solution. Thank you for watching.